Okay, can you hear me? Is that too loud or it's about right or is that okay? No, it's a real pleasure to be here. I was trying to remember the first time I came here was way back, and right after I graduated in '84, I came here. It was Barclay Jones, George Miley, Roy Axford, Jim, and a few others, but those were the four that I talked with, and I kind of look at now the growth over the years. I come back a few times, and it's really been impressive. And I think Brent, you're doing a great job. You and Rizwan and Jim and the other senior faculty, especially hiring some of the new faculty. So, congratulations. I also, came very close to joining the faculty here. Before I went to Michigan, I interviewed and actually had an offer. Things just didn't quite work out. But it's been a benefit to you because then you were able to get one of my best students. And what I'd like to do is to start off today with a very short Thomas Kozlowski story. Is that okay? All right. Here we go. So the story goes like this. Okay, so there we have like a lot of you have a sophomore level seminar course where all of the professors, they come in and they talk about what they're doing. And what we did is we just developed a code called Parks for the NRC. This is back, in the 90s, late 90s. Okay, so this was a talk to the sophomores, and I'm in there, presenting a little bit about parks and everything. And it's about 30 or 40 students. And there's one student, one sophomore, sitting back in the corner, reading the school newspaper. It was paper back then, right? So he had it wide open. And every now and then he would look over, and then just keep reading the paper. All right, so I had learned now, this had been at, Purdue for a while. I learned you can't reach everybody, right? You just, okay, it is what it is. All right. But at the end of the talk, I told everybody, all the students, I says, well, look, if any of you found, interesting what we're doing, come on by my office, and then we'll see if we can find some way to get you involved in our research. Okay. The last person I expected to come visit me the next day was the newspaper guy, right? Okay. All right. So he says, yeah, I'd like you to involve. Okay, well, let me go talk to my postdoc and see what I can come up with. All right, so I go down, and I talk to him, and I said, okay, so what's the most difficult problem we have? The most difficult problem we had is this one. Why are you not working? Oh, the laser's working, but the slides don't want to slide. Sorry about that. There we go. Is it working now?
It is.
Okay. Okay, so what's the most difficult problem we had? Okay, so we had developed the code Parks to couple with the systems code RELAP so that the NRC was going to be able to solve the coupled neutron, temperature fluid field for transients. And the transient they were interested in was this one. What we're looking at here, obviously, is the reactor itself. And it's a pressurized water reactor. This is the primary system, it's the secondary system. And, the primary system, right, the fluid here, okay? And what's going to happen in this particular main steam line break event, this line is going to rupture, okay? When that line ruptures, what happens then, the steam generator will eventually lose the water from the secondary loop, right? depressurized. So the water in the primary loop then is going to be, losing more heat than normal. It's going to get colder. Okay, so the water then that's coming back into the reactor is going to be colder than normal. Okay, so of course what we have is a negative moderator temperature coefficient. Negative negative means positive. Okay, so it's a positive reactivity insertion. Okay, so what was happening is the NRC was getting a lot of submittals for longer and longer fuel cycles, right? 13, 15, 18, 20-month fuel cycles. The longer the fuel cycle, the more plutonium and the fertile species in the plutonium that are building up over time. So therefore, the moderator temperature coefficient was getting more and more negative. Okay, traditionally they were using point kinetics in the relap code, but point kinetics wasn't doing a good job now predicting this event, and it was being overly conservative, predicting a return to criticality. So what they were interested in is coupling to the spatial kinetics code, PARCS, and then being able to simulate this event, okay? Because now they were gonna get a better, neutron flux distribution, okay? All right, so they said, all right, have at it. Develop a relap model, develop a PARCS model. Model this thing, it takes about 100 seconds for the steam generator to drain. And when the steam generator is finished draining, the event is over. But it's a long event. It's complex because it's involving the coupling of the neutron power distribution from PARCS to the temperature fluid distribution from relap. Okay, PARCS, relap. Perfect. Let's give this to the newspaper guy. All right. So next day he comes back in and I said, all right, here's the specs for the problem. This is an OECD benchmark problem. Here's the relap manual. Here's the PARCS manual. Have at it. And we never expected to see him again. 3, 4 weeks later, he comes back and he says, I think I got it. And I go, got what? And he says, well, I've got a model of relap modeling the core. So this is the core. Okay, these are all the channels. This is the PARCS model, every fuel assembly in the core, and then broken into 18 thermal fluid channels. Okay. And then what we're doing is we're mapping. This is the PARCS nodalization axially for every one of these fuel assemblies, and this is the relap nodalization. Okay, so you're going to be mapping this and doing this coupled field for 100 seconds, time stepping. Okay, very complex. Okay, I said it impressive, but does it work? Well, reactor scrams after the event, and then slowly, this particular scenario, what we do is we look at the power, return to power, and sure enough, he modeled it. Okay, all right. The rest is history. Thomas, I said, gee, he's good. We're going to keep him for, graduate student working with the group, and we did. And the story is, and then of course, and went to Sweden, taught at KTH, did there the stability benchmark. But the story is interesting because what happened is when he became a grad student, he's sitting in, down in the office working, doing his thesis research. And every now and then I would, have a young student would come up to me and said, well, I've got a problem here with my model or whatever. And I said, well, go see Thomas. He's really good at this. So he would go down and talk to Thomas, or at least, approach Thomas, tell him the problem. Thomas would look up at him and say, read the manual, except he would put an adjective, colorful adjective beginning with an F in front of manual. And the students would come back down And they were almost in tears. And you know, I guess it worked because then eventually a lot of them got it. So, you know, so I don't know if ever you're working with Thomas, RTFM. Okay. We have, this past summer, we had a reunion at Purdue. And, you know, this is interesting because, you know, after 28 years working for the NRC, continuously, you know, that's because I've always had really good people to, you know, do the R&D and the maintenance of the code. This guy here was actually the guy that first wrote the first few lines of the code, Han Ju. He's a professor at Seoul National, and he's now the president of KERI, which is the Korean Research Institute. This is Yoon-Lin Shu. He's a professor at Purdue. And then he took over for Han, and then Thomas. And then down here is Andy Ward. And Andy is now the current Parks guy. Okay, he's taking care of the code. And this guy here, this is the guy that wrote the code that I'm going to talk about today. It's Volkan Seker. He wrote the agree code. So, you know, again, over the years, I've been very fortunate in having such, you know, capable students, Parks first, and then agree. But there's one we did for Castle called Impact. You know, Michigan Parallel. I named these codes after wherever I've been. I guess not so with agree, but Michigan Parallel Characteristics Transport. And it's interesting, you know, the Impact code takes Parks another level. It does pin resolve. So now you're interested in no longer using a two-step calculation where you first compute the coefficients for the Boltzmann equation. Now what you do is you directly solve the temperature, fluid, and neutron flux equations together at every step. In other words, you're doing the resonance self-shielding in line. So that's Impact. And then again, this was one of the key codes in the Castle project. So what I'd like to do today then is focus strictly on gas reactors and advanced gas reactors. And you know, this agree code, you know, has been very important, you know, for industry, Keros, X-Energy, and it actually began, you know, being developed by the NRC, you know. And what I'd like to do is be giving you just an overview, okay? Because I'm going to show you how what is going on is agree is being used at all three levels of the Advanced Reactor Demonstration Project. X-Energy, Keros is part of this IPE, and then with MIT, we're working on a level 3. So I'll talk briefly about all three of these. What we're doing is solving, you know, the temperature, fluid, and neutron flux equations for two different kinds of HTRs. You know, one is the prismatic design, okay, which the triso particles are in these compacts, which are inserted into these blocks, okay? And the other is the pebble bed reactor, you know, where the pebbles are put into the core, and then they contain the triso in this tennis ball size, okay? So the agree code itself began as that one person I showed you, Volkan, began as his PhD thesis way back in 2005. And originally we developed it, you know, he, you know, was developing it for the pebble bed reactor using porous medium, thermal fluid solution, three-dimensional. And it was obviously doing steady state and transient for, you know, the various accident conditions. You know, that project was not funded, okay? We were doing it because that's what he wanted to do. And we were able to find, you know, GSIs and things like that for him. Then what happened is the NRC got application from the DOE NGNP program. And they funded us to develop AGREE as a prismatic, and they actually named it AGREE, okay? It stands for Advanced Gas Reactor Evaluation Engine. So we did that for several years for the NRC, and then most recently, the NRC has turned to the Moose Pack, or the Moose Package Pronghorn, and released us, okay, to create derivatives of AGREE to work with Keros, and then now with X-Energy. And we've also been using AGREE in collaboration with Argonne to look at the Magnox reactor. So what I'd like to do is to just show you, a little bit of the background on each of these, a little bit of the methods, and then talk about the applications in the ARDP program. This is the NRC's, what they call their evaluation model, and then the role that AGREE was going to play. This is their, plot, and they're looking at normal operation transient analysis, but obviously, ultimately, what they're interested in is the release and the Melcore code. Okay, so it was scale to Parks, AGREE, and then transient, and then supporting Melcore. What we did for the NRC, though, is we had to sharpen the modeling to account for some phenomena that happen in a graphite block system. Specifically, over the course of time, the graphite tends to deform, and what you get then is a lot of the fluid that you think is going to go through to cool the fuel is now going to go into these bypass regions. So we had to come up with a way of treating this cross flow, okay, or the bypass flow. Bypass flow is important. It's can be on the order of 15%, specifically further on into the irradiation. So that was one thing that we really had to work on. And the extensions we did for Keros about 2018, the original AGREE, then they put up prefix KP, Keros Power. Addition of fly properties, and fly, caused some special concerns. We had to start, treating the pressure temperature dependence of some of the coefficients in the momentum equation to handle fly, which is very temperature and pressure dependent. And then this is just a schematic of the FHR. The Magnox reactor, this one was really interesting. Oak Ridge was approached by NNSA. They wanted to be able to get, estimates of how much plutonium. This was a non-proliferation issue, so they wanted to find out how much plutonium was there in some of the Magnox reactors in the UK. And what we did is we then coupled AGREE to the MPAC code, which we developed. So that was, kind of, for us, nice symmetry. We developed MPAC, and then also now we were coupling it with this gas dynamics code AGREE. But the application that has been most satisfying, a lot of fun for us, has been X-Energy. X-Energy, we really have done 2 projects with them. One prismatic, one pebble bed. The pebble bed is the level 1 XE100. It looks very much like the pebble bed that's being built or is already built in China. So it's a we think a good technology, and we're helping with the design basis events necessary for the PSAR. This one here is the micro reactor, and originally, the X-Energy was part of the Pele project. BWXT, won the phase B, but now X-Energy is back designing a mobile reactor, and so we're involved in that work. okay? And it's for the Department of Defense. And unfortunately, I can't talk much about that or this one, but I will talk a little bit about this one here. So let me walk you through just a little bit on the methods. One of the innovations that we think we introduced was, using the Monte Carlo code Serpent to generate cross sections. Typically, codes like Casmo, Helios, scale package, Polaris were used. Deterministic codes have been used. But to overcome a lot of the complications of that, what we did is decided just to bring the hammer and generate cross sections. And this really had two advantages. We would generate, the cross sections, from using Serpent, pass them into our converter, right? Homogenized group constants into our converter, doing this in whatever, 8, 10, 14 groups, okay? And then do a deterministic steady state, but then transient calculation. Okay, so what the obvious benefit of this is if you could come down here now, and let's say you're doing some benchmark or you're doing some core calculation, the good news is you also have a full core Monte Carlo calculation here to then compare to the deterministic calculation, which used homogenized cross sections for each one of the fuel assemblies or pebbles regions, but using those. So this provided you with a self-consistent way of understanding some of the limitations of the deterministic core calculation, okay? So that was one of the benefits, of this technique. The core solution in Agree, pretty standard RZ theta stuff. We have both a nodal solver and a finite difference solver, okay? Temperature fluid equations, porous medium, solving for the solid, fluid, continuity, and then the momentum balance equation. And those of you that have done work, with HTRs, there's a lot of subtleties here. The temperature dependence of the conductivity, things like that. So you bring all of that into bear, the constitutive relationships. This is a slide I want to spend some time on because it's something that, I learned a lot. I've always been doing modeling and simulation, multi-physics. But where did we fit in the overall, risk assessment? And it's just, the probability times the consequences. So we've been looking mostly at the consequences supporting the release. But, everything begins with the PRA. Being able to find, what are the most probable events that I need to be concerned about for this reactor. So it starts right up here. PRA, leads everything. From that, then experts identify which are the important phenomena. Identification, identify them, ranking. So PIT stands for Phenomena Identification and Ranking Table. From that, then you get those that are highly important, okay? And then you make sure that those become the critical characteristics that you identify here, okay? And then make sure that your code can prove, so to speak, that it does these things within a given acceptance criteria. You got to prove that. And that's obviously what the NRC wants to see. So when we set out to do this is showing it for the pebble bed, what we identified, well, first of all, there weren't a lot of experiments performed for the pebble bed reactor. There were some, but not as many as there were for light water. Okay, but what was there was the HTR-10, which was a small 10 megawatt reactor built in China. HTR Proteus, built in Switzerland, okay? PBMR 400. Interestingly, this was a South African benchmark, but not an operating reactor, okay? So this was going to provide us with code comparisons. So let's say you got 10 countries around the world that are gonna have codes and they want to compare them. And then from that comparison, you can get a sense of what we can loosely call validation. And then SANA was a German facility where there was actually some tests. So I'll just show you very briefly each of those. One slide. This is SANA, okay? And it's just electric heaters in a pebble bed. So these heaters were used at different power levels, okay? And then Agree modeled this, and you see reasonably good comparison, okay? So this gave us confidence in just the temperature fluid calculation, okay? And then for getting the pure neutronics, you went to a critical facility, and this is the HTR Proteus in Switzerland, okay? There were many cores. We did, for this, we did 5, 7, and 8, okay? And, these are the different things that were measured. And the good thing about these experiments is that, like a lot of things the Swiss have done over the years, it was very well measured, very, very good instrumentation. So again, we modeled this with Agree, compare the results. This is Agree with serpent cross sections, and you can see that we are within our acceptance criteria. Okay, so that's the temperature field, the neutron field, and now what we did is, the coupled temperature fluid field, and that's HTR-10. So this was a IAEA benchmark test done back in about 2003. And they did a bunch of steady state coupled field, and then they did some transients. Did a ATWIS transient benchmark. And you can see these are the comparisons for the steady state. There were some thermocouple measurements, different Rodworths, critical height, okay, reactor activity coefficients, Rodworths, things like that. And then this is a experiment they actually did, the ATWIS, and then seeing the return to critical, okay? And again, the experiment and then the Agree, and turns out that that's not too bad. So that is giving you a sense of what's necessary to, to satisfy someone like the NRC, that your code is capable now of being used in the safety analysis of an entirely different machine than those benchmarks. But you've demonstrated that you can get certain critical characteristics that were available through experiments. I'm not going to take you through the prismatic, but the prismatic also has benchmarks. The HTTR, this is a Japanese reactor, 30 megawatt reactor, and after Fukushima now, it's back operating, and they just completed another test. They did an loss of force convection. And there's benchmarks, MHTGR benchmark. This is just a code, much like the PBMR 400 is. But there are other experiments, Hendel, SNU bypass. These are just thermal fluids experiments. And the issue there is a lot of importance on bypass flow. Can we predict that fluid that's going between the blocks? Okay, so that gave us confidence in our ability to model, the HTR for both the pebble bed, and for the, prismatic. And so now I want to walk you through, some of the applications. The first one, for those of you familiar with the ARDP program, it's about $1 billion in total. Okay, and then the level ones, there were 2 companies chosen, TerraPower and X-Energy. And then they're getting on the order ballparkish about, 80 million a year. And the target date is 2027 for them to be able to, demonstrate the buildability. And the target place for the XE100 to be built is a Dow chemical plant in Texas. So I want to, first start. Well, I just said some of this. Advanced reactor demonstrations, 7 years. We started about 220, so about 2027. Level 2 is a risk reduction for future demonstrations, and this is one that Keros won. And then level 3, this is advanced reactor concepts, which will support innovative and diverse designs. And so the next slides I'll show you what we're doing with MIT. They have a level 3. This is the concept, again, led by, this is Karush Shravan. He's the PI for the project. And it's a horizontal gas-cooled temperature reactor. Prismatic blocks. I'll show you a layout of those in just a second. But the idea here is reduce construction costs. I'm going to show you we're using no longer just control rods. We're using drums, controlled drums, to reduce the overall length of the machine. But the design is MIT's. They came up with it. We're co-PI because of Agree. They need our code to deplete to do the transient analysis. Okay, so what we're looking at here, this is the core itself, and then this is the loading pattern. Okay, so these are all, these graphite fuel blocks, and you notice they're in the form of squares. Okay, and the reason for that is that they're on their side, so to speak. So better than having a hex with a small side, now you get a square. So they're on their side, 2-batch core, 2-batch core. And these are all drums, control rod drums, where the outer layer, see this part here? See, that's got the control absorber, all right? And when it's facing in, obviously, it's, acting like a control rod, would, shutting down the reactor, or during depletion, handling, some of the excess reactivity. And then what you're looking at here is just a axially integrated, power distribution. When the drum rotates in and the drum rotates out, you can see a little bit change in the power distribution. Okay, so this is a project we're doing with them, and we're in our 3rd year, and it's been a lot of fun. And what we've actually been doing is, having a senior design projects. So they just, in fact, emailed me yesterday that the group of seniors, they just went to the senior design conference in Penn State, and the ones that did this got the best paper, best presentation award for reactor physics. So that was great. I mean, I really felt good about that. And the nature of their project specifically was, find the best loading pattern for these blocks. See, you've got, two batches of fuel, fresh and burned. Okay, and then you've got the degrees of freedom, not just radially, but these are stacks. Okay, so when you do the factorial, it's unmanageable. So they've developed, simulated annealing algorithms, and they came up with some pretty neat stuff. So feel good about that. Okay, this is a level 2. We supported Keros for the FHR, as part of the development, of the design and development of their FHR, but they don't want me to talk about that, okay? Because they're in the process of licensing, preparing their licensing. Instead, we also have a project. We have an RPE project with them. And the RPE project, what we did is we have a sanitized, we called it the GFHR. And we work with Argonne, who's one of the collaborators on this project. And what they're doing is using the SAM code. See, so we have, again, Serpent agree, and then we're, the highest fidelity, and then what we're doing is generating, the kinetics parameters for SAM, and then SAM then is training a digital twin, okay? So it's broken into a bunch of tasks, okay? But, one of the innovative parts of this is, just seeing, how good can you get, with the digital twin. And what we're interested in is, looking at, specifically a load follow event. Because when you're working with FLIBE, and I think many of you know this, FLIBE is a very, it's convenient, it's heavy, it doesn't disappear like water, and it's very effective in its ability, and not absorbing a lot of neutrons. The bad news is the pumps are working pretty hard. And when you do load follow, you're going to follow by keeping the outlet temperature constant and changing the flow. And so pump degradation is a big deal. Okay, so that's one of the things we wanted to do. And INL has people that are working on this project, and then they have software that does deep supervisor, and then this one is maintenance proactive evaluator. Okay, so the digital twin is really the part that I thought, I'm really, old dog learning a few new tricks. I wanted to see if this could really work, and I've been surprised. This is a schematic of the FHR, GFHR. Okay, and what we have is, again, a SAM model of all of this, and then just an agree model of all of this. We put features into the agree code. When we move a control rod in agree, what happens is the power distribution changes significantly. No surprise. But that's some information that we want to get to SAM. So what we've done is put a form function into SAM. So a few extra things we had to do. But again, the digital twin, task 1, and the person doing that is, he's not a nuclear guy. He's Aero, Kartik Durasamy. Okay, and then my task is to, kind of pull it all together. Rick Willem from Argonne has been doing the control module, and then Humberto Garcia from INL has been doing the NPE and the ODS. But again, the key player has really been the digital twin. The idea here is it takes, many, many minutes for SAM, to do a simulation. We want to get a digital twin to do it in milliseconds. And it's been successful. This is a schematic of how the pieces fit together. Again, we're led with Serpent. We model the FHR with serpent-agree. Okay, and then what we do is we generate, the reactivity coefficients and everything we need in SAM. And then this goes off and then trains the digital twin. Okay, and then the digital twin is then available to task, 2, 3, and 4, to apply it. The pump degradation has been, the centerpiece of that. I have a plot, a very busy plot of all of how well the digital twin agrees with SAM and everything else. It's too busy. Instead, all I'm just going to do is just show you a core load follow the simulation that we're doing. And then the idea is this, is we really are interested, in yes, sacrificing, some accuracy, okay, but getting these runtimes down, okay, and having a runtime down here that has, again, allowed us to do an investigation of the, degradation of components. That's the idea, okay? Okay, so that's level 2, and then level 1, this is the XE100, and they're in the middle also of doing their PSAR. As we speak, it's still being written. Can't talk too much about that because they don't want us to, get stuff out there that maybe is going to change. And, so I'm going to talk about the events that we're doing, okay? But I'm going to do it within the context of the PBMR 400, which is very, very similar. What we're doing for them is, again, out here, agree. We're taking, VSOP, which is, historically, it's a code developed 60s, 70s for the pebble bed reactor, Germans. And basically, it depletes, takes pebbles, runs them through about 6 times, okay? And then what we are talking about is getting a equilibrium core condition, getting the isotopics for this equilibrium core condition, and then taking that and running serpent. Because what we're interested in is that state point, right? Or the equilibrium core state point, and then doing transient analysis with agree, okay? All right. So this is, again, the schematic of the core. And I'm showing you here then, this benchmark, the PBMR 400, okay? And for those of us that, spent their career like I did, in light water, this is really a change of perspective because now what we're looking at is, 100 hours. Ride this thing out 100 hours because we get a return to criticality about 50 hours. And I will say that we also get it with the XE100, but it happens. And the physics of that are really interesting. And you can see it down here with looking at the reactivities, okay? What you get is the total reactivity comes down because you got your Doppler, that comes down, okay? You have the moderator reactivity gives you negative, negative. But what's happening is the xenon, right? The xenon reactivity, this line here, right? The xenon is now decaying. It's no longer being absorbed now by, the flux, right? It's decaying only. And that decay of the xenon then gives you this large positive reactivity insertion, which xenon half-life, 8, 9 hours, and there's about 8 hours. It takes several half-lives, and then you've got sufficient xenon reactivity that you have a return to criticality, out here. That positive overcomes all of these negatives. What you're interested in is, again, you're interested in things like maximum temperature. And for this is the PBMR 400. So this is code, code, code. Several codes compared maximum temperature over time, and you get a temperature in the range of the 1650, close to 1700, okay? So that's the depressurized loss of force convection, which is one of the design basis events, okay? Okay, last event I'm going to talk about is the seismic event, because this for me was really interesting. Things I never thought about. I've been doing this for 40 years, right? Okay, but most of these years were spent with water. And now here comes graphite, and I go, okay, no problem. But then you start to look at design basis events. And one of the more interesting ones, and everybody had, when they were a kid or so, they have a jar of marbles, right? And you know that what happens when you shake the jar, what happens? It compacts, right? And when it compacts, you think, okay, I'm going to get a reactivity change. I mean, something's going to change the physics, right? But I'm thinking, resonance escape probability goes down, right? So that's going to be a negative. And sure enough, that is a negative. But I didn't think about something else. I didn't think about that the height of the pebble bed is reduced. And what I have is I have a couple control rods partially inserted. Okay, so what happens, okay, I'm one step ahead of myself. Let me go to this one here. What happens, the control rod is here and the control rod is going to stay put, right? Okay. And this is the pebble bed and you got an upper cavity here, but you shake this and your compaction, can go from 61 to 64%, let's say, okay? And what you're doing is you're exposing a piece of the control rod here. And I said, well, yeah, but that's not much, right? I mean, it's only, 40 some centimeters here, right? The problem is that the power distribution is top peaked, okay? Because the fresh pebbles are coming up at the top. So what happens is this chunk here is what's getting exposed, and that has a higher worth because of the higher power up there. And lo and behold, what we found is that the reactivity insertion, even with the negative on the resonance escape probability, the net reactivity effect is more than $1, which makes it a concern. Maybe, okay? What also they had available is this is a shaker table experiment done in Germany. And this shaker table, just, simulates an earthquake, And what they found is what is the compaction, over time. And it takes, many minutes to get from 61 to 64%, okay? So we're not looking at, in this case here, we're not looking at something like a control rod ejection, in a tenth of a second. Instead, what we're looking at here is something over many minutes. Okay, so the eventual reactivity is more than $1, but it's a ramp. And then during that ramp, obviously what's happening is you're getting feedback, which is keeping you subprompt critical. Okay, so that's the net effect of it. But I mean, I guess me personally, at this point in my career, just learning something new, playing with some new, scenario and feeling that, hey, this is interesting. So in summary, the Greek code models a couple neutron temperature fluid field for both pebble bed and gas. Agree has been extensively verified and validated using both experiments and code, and is supporting both the government and industry, and we're very, very proud of, that because, to get a code, to that point, it's not, we're working on commercial grade NQA1 designation, but, the fact is to get to that point, whereas a university, we're able to do that. And we did it with parks, okay? But to do that, and to be able, to help Keros, to help, X Energy, and of course the NRC, and then involve students. You see, we're having an impact, okay, now on all levels of the RDP, and this is something that I think it's really possible to do, okay. And I guess Thomas didn't mention, but the other thing is, I'm retiring in June. 40 years, that's enough. And I look back, and I got to tell you, when I was your age, sitting there, I always had some doubts. Is this a good field to be in? Because in my case, TMI just happened. Okay, and I go, huh. And then I looked at that and I says, well, maybe it is a good, get in the market low, so to speak, and because it still needed some good people. And I think now those days, the Fukushima days and everything else, I think are they're behind us in a way. But now, seeing that, okay, you guys are in a field where the potential is obvious, okay? And a lot of people out there don't know it, okay? But the potential for nuclear to really help with climate change. So if I saw myself now sitting where you are, listening to this old guy talk about what he did for 40 years, I'd go, yeah, maybe. But I'm encouraging you, hang in there. And I think you're really going to see, that nuclear is going to be, the solution. Part of the, one of the programs that is really going to help climate change. Thank you. Any questions? Please.
You have a plot that you have to sacrifice that accuracy. I wonder if you get us like some example of what things that you sacrifice, like the medical methods or like the physics.
Yeah, you're the expert. But what we have found is that there are some things, especially when there's like a step change. When we change the power over here, when we make this dramatic change in the power, okay, what happens is Varmax or some of the routines, they reach back 4 steps or something, and you can't do that after you get a step change, you see. So that those instantaneous things that you can do. Now, the good news is you don't change your power like that fast. You see, physically, there's a ramp rate in the power that is slower, okay? But nonetheless, we find that, the digital twin doesn't do well, for things that are short in time, okay? As far as accuracy compared to SAM, we found that, it's remarkable what they're able to do. This is a load follow, so this is a very simple, well, I shouldn't say simple, but it's just one case. And obviously what we're interested in is, what can we do for transients? See, take a transient and be able to model that. You have to add, explicitly things like xenon samarium. You gotta do a lot of other things, but okay. That'll maybe slow it down from a millisecond to, a little bit longer. But you're right though. I mean, there's a lot here, but Kartik Dursamy is our expert, and you know the field. So, any other questions or comments? Yes.
Thank you for going over the action. It's very interesting. I was wondering the experiment that you showed.
The shaker table. Yeah.
Is that in air or a prototypic helium environment?
That's not helium. No, that's open. Yeah, I don't know that facility. It was way back, but my understanding, it was just open, to the air, and they were just shaking, with the table. This was a very tough reference to find, I'll tell you. Okay. I never heard of this conference. All right. A seismic behavior of the pebble bed in an HDR plant. It was a very difficult, reference to find, but that's all there was. How good is the data? And what does this data buy you in terms of, we're talking about building, the XE100 in Texas. Okay. In Texas, they're not going to have, I think, many Richter 7 or 8s, you see. And also, this was done, with a very steady, shaking rate. But the way earthquakes go, that can be a little bit random, right? It can start, stop, aftershocks, things like that. So it's really more just trying to get arms around the problem. But to answer your question, I don't know all the details on this. Okay, the paper.
Still on the same topic, I was curious, did you do any sensitivity to see whether conclusions change when you change the speed of the ramp or the extension of it? Because I'm thinking, graphite, especially the one that contains the fuel inside, is very brittle. So it breaks, it crumbles. So potentially, if you have a high impact earthquake, it could also increase even further the vacuum fraction, because at that point, since it breaks, it does occupy all the space in between. So the question is, if you increase the extent, so instead of getting to 64%, you get to even more, or you make this phenomenon happen faster, do you still see the decrease in reactivity after some time?
Yeah, we haven't looked at cracking pebbles. What's the probability of that? I don't know where Zara is. Where is she? I don't know. But I gotta imagine that, that's probably outside. We're taking our marching orders from X Energy. All right, do this, this, and this. Have they been looking at actually cracking the pebble? If they do, yeah, we got more issues, but you make a good point. Yeah, but the answer is, I don't know.
So same topic. So a reactor that during an event can go prompt critical, that's not good. I guess I would come to I understand the timing part of it, but obviously one solution is you have rods during operation that are further down. But I would think that any regulatory agency that saw the word prompt critical in an event would.
Yeah. Okay. This is a little bit deceptive, because this is not, you're not going super prompt, as I mentioned. The reactivity over time, okay, so it's an integral of the reactivity over time from the shaking, okay, and then the corresponding, negative, but the feedback is not in here. There's no, yeah, well, that's the part, it's inherent, you don't have to worry about. It doesn't go super prompt. And the reason it doesn't go super prompt is because over time, as the power is increasing, you're getting the negative feedback. But you're absolutely, right, Brent, that, the NRC wants nothing to do with super prompt. Okay, so please don't take away from my discussion here that we went super prompt. I'm saying that, the reactivity insertion, okay, that we're getting, and I have to maybe clean this slide up then, okay? So good point.
If I may, one other thing about the slide, so, how are you dealing with the technical data gaps related to physical properties when you're doing modeling? Like density, temperature, dependence of density, and total conductivity for the fly. Is everything, you have all the data you need for the properties?
Oh, gee. Well, all we're doing with Agree is we're taking what we have, and then we're treating it, to the, the fidelity we need, which is, again, like I mentioned, we're having to modify and create derivatives of all of the properties as a function of temperature and pressure. Do we have the right functions? That's another question, and maybe April might help with that a little bit, but I'm just taking what we're given and we're using it, so. Okay. Thanks very much.